So today we are going to talk about the reflection of waves, then stationary waves and beads. Alright, so let's begin. So first of all, let's see reflection of waves. So suppose there is a wave which is going from a rarer medium to a denser medium. Okay, so this wave is moving from a rarer medium to a denser medium, and this is a transverse wave. So see, here suppose we have this string and then it's connected to a rigid support, and suppose I make it oscillate. Then what happens? This crust formed on the string, it travels along the medium and it collides on the boundary of two media. Okay, this crust formed, it collides on this wall, and from there it gets reflected back. Okay, now see, this crust, it's moving in right direction, okay, towards right, in positive x direction you can say, and it goes till this end. Now what will happen here? So let's understand. So here you have particle of this denser medium, that is the wall, suppose. So this particle, consider one particle. Now this particle is pulled by this wave, okay, meaning the particle is pulled by the string. Okay, so this particle of the wall, it is pulled by the string or rope in upwards direction. Okay, so the rope exerts some force on this particle of the denser medium. Now what will happen? The particles of denser medium, they will also exert equal and opposite force. Okay, and because of that, see, the particles of denser medium, they exert equal and opposite force on the rope. So now what happens is, the rope is rarer, okay, and this is the wall, this is rigid. So the particles of wall don't move, but what happens to the particles of rope, or let's say rope itself? So because it is being pulled by the wall in this direction, in downwards direction, so this crust becomes a trough because it is pulled down. Okay, and it gets reflected back as a trough, right? Okay, so crust moving from a rarer medium to a denser medium, it gets reflected back as a trough. Okay, so if there is a transverse wave moving from a rarer medium to a denser medium and there is a reflection of transverse wave, then what happens? Crust will get reflected as a trough, and similarly you can say the trough will get reflected as a crust, right? So see, suppose this is the equation of a traveling wave, okay, T for traveling, and the equation is a sine of kx minus omega t. So that means it is traveling in positive x direction. Now what would be equation of a reflected wave? So reflected wave will travel along negative x axis. So the equation would be a sine of kx minus kx plus omega t. This minus sign will become plus. Okay, so this wave travels in negative x direction, but then there is change in the sign of the sine function. Okay, so we put a negative sign to indicate that there is shift of phase by 180 degrees or pi radians. Okay, where does it come from? So crust gets reflected as a trough. That means there is shift in phase by pi radians or 180 degrees. So this thing is clear? Yes, no? Everyone? Right? So this is a reflection of transverse wave from moving from rarer to denser medium. Next, let's suppose a transverse wave is traveling from a denser medium to a rarer medium. So suppose we have the string, and the other end of the string, it's connected to a hoop or a loop you can say, and this is suppose a plastic loop. Okay, it's very rarer compared to that of the rope. Then now what will happen? So the crust, it's moving towards right, it arrives at this end, and this loop or hoop you can say, it passes through this bar and it can slide freely, okay, up and down. So now when this crust reaches the other end, what will happen? The rope will exert the force on the hoop, okay, in this direction, right? And according to Newton's third law, the hoop will also exert equal and opposite force. But now the rope is heavier much heavier compared to that of this plastic hoop. Okay, you can imagine it to be weightless, right? So therefore the hoop is lifted up, okay, because of the force exerted by the rope, but rope does not move down, right? Because force is just not sufficient to move it down. Okay, so because the body that's exerting force, it is getting lifted up itself, and therefore what happens, this crust will get reflected as a crust only. Okay, so since hoop is lifted up, so crust is formed there. Okay, and crust is reflected back as a crust. Similarly, a trough will get reflected back as a trough. So suppose this is the equation of an incoming wave, yt is equal to a sine of kx minus omega t, right? Then what would be the equation of reflected wave? So crust gets reflected as a crust, but it just travels in negative x direction. So this is the equation of a wave moving in positive x direction, that is a sine of kx minus omega t. So this minus sign will become plus. Okay, this negative sign will become positive. Okay, so you have a sine of kx plus omega t, right? This is the equation of a reflected wave. Okay, so there is no phase shift now. This thing is clear. So next, let's talk about the stationary waves. Now what are stationary waves? So stationary wave means steady wave. Stationary waves means steady waves. So they are trapped in some region of the medium. Okay, and how do you trap them? So for an example, suppose you have the string and it is tied between these two ends, these two walls, and you give some oscillation. So you pluck that string and you release it. So some random oscillations will be set on the string, right? Several oscillations of different frequencies will be set on the string. But now what will happen? Suppose a crest of one oscillation reaches this end. What will happen? It gets reflected as a drop. Okay, because it's like a wave moving from a rarer to denser medium. Then the trough travels this way, it comes this end, so it gets reflected as a crust. Okay, so here what happens is several oscillations will be set, but then only some oscillations will remain and others will die out. Okay, other oscillations will die out, right? So we'll see which oscillations will stay there. So see, as you can see, these two ends are rigid ends. So what would be the deflection of these particles, displacement of these particles? Displacement of these particles would be equal to 0, right? Because rope is tied to this rigid support at those two ends. So the displacement of these particles is equal to 0, and that means these particles of the rope, they are not displaced. Okay, this is a transverse wave. So these particles are not displaced. These particles have minimum displacement. They are known as nodes. And particle over here, it will oscillate like this. Okay, you can imagine this is a one loop. Okay, so particle over here, it will oscillate just up and down. So the wave will look like this. It will just move up and down like this. Okay, so it's not moving anywhere. That's why it is known as a stationary wave. So for this particle, what is the displacement? So displacement is maximum for this particle, and this one is known as antinode, denoted by A. Okay, so these particles having minimum displacement are called as nodes, and particles having maximum displacements are known as antinodes. This is clear? Okay, all right. So now see here, suppose the string is plucked. Okay, so now it's like there is a wave which moves in positive x direction, and from the other end it gets reflected back. Okay, so there is a wave coming from left to right and a wave going from right to left. They superimpose, right? They superimpose on each other, and that's why some pattern of waves is formed. Okay, so what is a stationary wave? There is a wave which is moving from left to right. It strikes on this denser medium. Let's say there can be a rarer medium too, but suppose these are denser medium. Okay, denser media. So this wave, it is moving along the string towards right and it gets reflected. So there is an incoming wave and a reflected wave. So this is suppose the equation of incoming wave, a sine of kx minus omega t. This is the equation of reflected wave, a sine of kx plus omega t. What would be the resultant displacement? So this is displacement produced by first wave, this is displacement produced by second wave at some point, okay. These two waves are superimposed and the resultant displacement would be equal to y1 plus y2. Then what is y1? A sine of kx minus omega t. What is y2? A sine of kx plus omega t, right? And then now you can just make use of that formula. Okay, sine of a plus b is sine a cos b plus cos a sine b, and sine of a minus b is sine a cos b minus cos a sine b, right? So your a is kx and b is omega t. So using that formula, you can write sine kx cos omega t minus cos kx sin omega t. That is the expansion of sine of kx minus omega t. And similarly, expansion of this one, sine of kx plus omega t would be sine kx cos omega t plus cos kx sin omega t, right? So here you can see this term cos kx sin omega t and cos kx sin omega t, it gets cancelled out, right? And what remains is sin kx cos omega t plus sin kx cos omega t. So you have 2 times of, okay, a into sin kx cos of omega t. So this is the equation of a resultant wave which is trapped between those 2 points, okay, and we write it as y is equal to r cos of omega t, okay, y is equal to r cos of omega t. So notice here there is no omega t minus kx or omega t plus kx term. So that means wave is not moving, okay. If wave is moving in positive x direction, there would be omega t minus kx term. If it moves in negative x direction, there would be omega t plus kx term. So this wave is not moving, okay. This thing is clear, everyone? All right. So now then you have r equals to 2a multiplied by r equals to 2a multiplied by sine of kx. See, r here is the resultant amplitude. So y is equal to 2a sine kx cos omega t, and here this term, okay, gives the resultant amplitude, that is r. So r is equal to what? 2a sine of kx. So now see, all points on the string, they are oscillating with frequency omega and amplitude is equal to r. R is different at different locations, right? All points, they are just oscillating, all points on the string, of the string, let's say, they are just oscillating with amplitude r, but r is not constant like ordinary waves. Ordinary meaning traveling waves. R is not constant, r is a variable here, okay. So r is 2a sine of kx, right? So some points don't oscillate, that means r is equal to 0. So they are called as nodes, okay. What are those points? So put r equal to 0, okay. If you put r equal to 0, you will get those points. So for an example, at x equal to 0, you have a node. So if you put x equal to 0 here, you get r is equal to what? This thing is sine 0, sine 0 is 0, 0 multiplied by 2 is 0. So you get r equals to 0, right? And then, so if you want to find out position of nodes, then you have sine of 0 equals to 0, sine of pi is equal to 0, sine of 2 pi is equal to 0, right? Sine of 3 pi is 0. So I can say sine of n pi is equal to 0, okay. So that means we have sine of kx in the amplitude term, right? Our amplitude is 2a sine of kx. Sine of n pi is equal to 0, means kx must be equal to n pi at the position of nodes. Nodes mean 0 amplitude, okay. So kx is equal to n pi, then put n is equal to 0, 1, 2, so on and so forth. So if you substitute that, what do you get? So substituting that and substituting k is equal to 2 pi by lambda, okay, and cancelling out pi, you get x is equal to n times lambda by 2, okay, n times of lambda by 2. So first node will be formed at 0. X is equal to 0. Right? First node will be formed at x equal to 0. Next node will be formed at x equal to lambda by 2. Okay, n is equal to 1. Then next node will be formed at n equals to 2. That means x equal to 2 lambda by 2 means lambda. So what does it mean? If there are only two nodes, so first node is formed at 0, second one is formed at lambda by 2. So string will oscillate like this, forming one loop. If there is one extra node, so that means the string will oscillate like this, forming two loops. Okay, so first node will be formed here 0, second node is formed at lambda by 2, third node is formed at 2 times lambda by 2 means lambda. So you can see here one crust and one trough. This is a wavelength. Okay, so if two loops are formed, if string oscillates forming two loops, that means the separation between start point and end point is equal to what? It is equal to lambda. Okay, this thing is clear, everyone? Right? So what is length of one loop? Length of one loop is equal to lambda by 2. Okay. So these are positions of nodes. What would be positions of antinodes? So similarly, now we want this sign of kx to be maximum. Okay, and it will be maximum at what? Kx equal to 90 degrees, 270 degrees. Okay, that is pi by 2, 3 pi by 2, 5 pi by 2, so on and so forth. Right? Okay, so then we have sine of 2n plus 1 pi by 2 is plus or minus 1. Okay, so there you will have a maxima. So plus 1 is also okay, minus 1 is also okay. Because of what? Because see, the amplitude is positive or negative, but its phase will depend on what? This cos of omega t factor. Okay, so this cos of omega t will determine whether the particle will move up or down. So plus 2a is okay, minus 2a is also okay, right? So at the antinodes, the amplitude is plus 2a or minus 2a. Okay, I mean the magnitude of amplitude is 2a, right? It will just move up or down. Alright, so we have kx is equal to 2n plus 1 pi by 2, and so we have k equals to 2 pi by lambda. Okay, 2 pi by lambda times x is equal to 2n plus 1 pi by 2, and then pi and pi gets cancelled out, and then we get, see that this 2 will go in denominator. Okay, and then we have x is equal to 2n plus 1 lambda by 4, right? So either x is equal to lambda by 4 or 3 lambda by 4 or 5 lambda by 4, so on and so forth. So if there is a node at x equal to 0, then where is the first antinode? First antinode is formed at x equal to lambda by 4. Okay, so what is the separation between a node and antinode? It's lambda by 4, right? Separation between a node and adjacent antinode, it is equal to lambda by 4. Okay, this thing is clear? All right, good. So then next let's talk about the modes of vibration of a string. Okay, modes of vibration of a string. So what are modes of vibration of string? So see, the string can vibrate either forming one loop or two loops or three loops. Those are just modes of vibration of string, because more is the number of loops formed on the string, more is the frequency. Okay, lesser is the wavelength, means more would be the frequency, right? So now what is a harmonic? There are few terms. First is harmonic. So it is a multiple of fundamental frequency. Okay, so f is suppose the fundamental frequency. What do you mean by fundamental frequency? F is the frequency of first mode. The frequency of first mode is called as fundamental frequency, right? It's the minimum frequency with which this string can oscillate. Okay, so let's find it out. So see, this is the fundamental mode. It will look like this. There will be only one loop formed between these 2 points. Okay, so string will vibrate forming one loop, and then you have V is equal to f times lambda. Suppose f is the frequency of fundamental mode, right? Then see here, this lambda can be written as, see, length of the string here would be equal to what? Length is equal to lambda by 2. So what would be lambda? Lambda is equal to 2 times L, right? Since length is equal to, length of the string is equal to lambda by 2, lambda is equal to 2 times of L. Okay, you can substitute that here. So you get V is equal to f times 2L, or f is equal to V upon 2L, right? F is equal to the frequency of fundamental mode, it is just V divided by 2L. Okay, but what is V? So V is equal to, we know it from last lecture, that it is equal to square root of T by mu. What is T? T is the tension in the string, and what is mu? Mu is mass per unit length of the string. Okay, what is mu? Mu is mass per unit length of the string. T is the tension in the string. Then the speed of the wave that travels on the string, it's equal to what? Square root of T by mu, right? This thing is clear, everyone? So fundamental mode has a frequency of 1 upon 2L square root of T by mu. Okay, good. All right. So fundamental mode has frequency of 1 upon 2L square root of T by mu. Okay. So then let's see the second mode of vibration. So this is the second mode of vibration. So here string forms two loops, right? This is second mode of vibration. Here the string forms two loops. Okay. So see here, how much would be the length? So length of the second mode of vibration is just equal to the wavelength, and we'll call this wavelength as lambda 2 because this is second mode of vibration, right? Let us call this wavelength as lambda 2. So what would be the frequency of the second mode? So f2 is just equal to V divided by lambda 2. Okay, and what is lambda 2? So lambda 2 is just L, right? We have seen lambda 2 is equal to length of the string, right? So just put that. So you get f2 is equal to 1 upon L square root of T by mu. Okay, and this f2 is just equal to 2 times of f, because what is f? Frequency of the fundamental mode, it is 1 upon 2L square root of T by mu. Okay, this is frequency of the fundamental mode, right? So this f2 is equal to the second harmonic, right? f2 is equal to second harmonic because it is just equal to 2 times of the fundamental frequency. This thing is clear, everyone? Okay, and now see, in vibration of the string, this is the first frequency higher than the fundamental frequency, so this is known as first overtone. Okay, this is the first frequency higher than the fundamental frequency, so this is known as what? First overtone. Okay, so what is an overtone? Overtone is a first frequency higher than the fundamental frequency, it's known as first overtone. Okay, second frequency higher than the fundamental frequency would be known as second overtone, so on and so forth. So see, in case of vibration of a string, first frequency is 1 upon 2L square root of T by mu, second frequency is 1 upon 2L square root of T by mu, right? First frequency is what? 1 upon 2L square root of T by mu, second one is 1 upon L square root of T by mu. So this is the first frequency higher than the fundamental frequency, and that's why this one would be called as first overtone. So what is first overtone here? It is second harmonic. Okay, first overtone here is second harmonic. This thing is clear, everyone? Right? Okay, good. So then next we can see the third mode of vibration, and in third mode here you can see the 3 loops are formed, and therefore length of the string would be equal to what? 3 times lambda by 2. Okay, but the wavelength of third mode, we'll call it as lambda 3. So it is 3 times lambda 3 by 2, and therefore we get lambda 3 is equal to 2L by 3. Okay, and substituting frequency equals to V by lambda, that is V by lambda 3, we'll get in place of lambda 3 we'll substitute 2l divided by 3, right? So we get f3 equals to 3 by 2l square root of t by mu. Okay, so this is just 3 times of fundamental frequency, right? This is just 3 times of the fundamental frequency, and this is third harmonic. Okay, what is this? This is third harmonic. This thing is clear? Okay, so here we can see that in case of vibrating string, the frequency of nth mode is just equal to n times of fundamental frequency. Okay, frequency of nth mode of vibration is just n times of fundamental frequency, right? Okay, good. So all harmonics are present, meaning there are odd harmonics also as well as even harmonics also. Okay, so in case of vibrations of string, all kinds of harmonics can be produced. Even harmonics, odd harmonics, all are present. Okay. Okay, so then there is an experiment called as a sonometer experiment. Okay, and what is that? So in this sonometer experiment, you want to find out the unknown frequency of a tuning fork. Okay, this tuning fork will have some frequency which is unknown, and that you need to find out. So what you do is you load this string with known load, that is tension would be known. Okay, tension is just equal to this load. Okay, then what you do, you put a paper on top of the string. The vibrating length of the string is between these two wedges. Okay, the string is pivoted over these two wedges, right? So the vibrating length, the loops will be formed here, and then on top of that string you put a paper. Okay, small piece of paper. Then what happens after that? What you do, you take tuning fork, then you make it vibrate. Okay, that means you hammer it on a rubber pad, keep it over here, then this wooden board will vibrate and the string will also vibrate, okay, with the same frequency. So then now the frequency of tuning fork is equal to the frequency of natural frequency of vibration of this string, then the string will vibrate with maximum amplitude. Okay, and if it happens, then the paper will fall down. Okay, so you perform this experiment, and then what you do, you move these wedges till the time the paper doesn't fall down, right? That means the string doesn't vibrate with what? Maximum amplitude. Okay, right? So then using this formula you find out the fundamental frequency of the string, which would be equal to the frequency of vibrating tuning fork. This thing is clear? Next, let us see the reflection of longitudinal waves. So see, reflection of longitudinal waves. So here the medium would be divided in compressions and rarefactions, right? So now consider a longitudinal wave moving from rarer to denser medium. So there would be compressions and rarefactions. Suppose compression in this wave, it hits this denser medium. So what will happen? So what is compression? The particles are coming close to each other, right? Okay, particles are coming close to each other. Okay, so here you can imagine, see, compression is where the density is more. That means these particles, they will hit the particles of wall. Okay, they will exert force on particles of the wall. What happens then? The wall also exerts equal and opposite force. Wall meaning particles of wall, where they collide, they also exert equal and opposite force. Okay, so if a compression is there, then what happens? It gets reflected as a compression because these particles will be compressed further by the wall, right? This thing is clear? Okay, so if there is a compression, it gets reflected as compression, and if there is a rarefaction, it gets reflected as a rarefaction. Okay, so there is no change in phase of the reflected wave. We need to remember this. There would be no change in phase of reflected wave as compression gets reflected as a compression and rarefaction gets reflected as a rarefaction. Okay, this is contrary to the transverse wave hitting the denser medium, right? Now then you can imagine a transverse a longitudinal wave traveling from a denser to rarer medium. So this is a longitudinal wave, it's traveling from a denser to rarer medium. Okay, and suppose there is a rarefaction at this end, it hits the rarer medium, or you can imagine compression. Let's imagine compression. Okay, it hits the rarer medium. Now what will happen? So compression meaning these particles, they are coming close to each other. Okay, so there are more number of collisions in compression. So here in this compression, okay, this compression hits the rarer medium. So these particles of the rarer medium, see, these are particles of rarer medium. So this compression has some space to travel into the rarer medium, right? This thing is clear. This compression has some space to travel into the rarer medium. This compression can enter the rarer medium, okay, because density over here is very small, right? So the compression will enter the rarer medium, and what will remain there if compression enters the rarer medium? Rarefaction will remain. Okay, in case of rarefaction, what happens? The particles are going away from each other, so density would decrease there. So these particles at this end, they are entering, suppose, the rarer medium. Okay, these particles are entering the rarer medium, they are going away from each other. So what will happen? These particles are entering further into the rarer medium, so what remains there would be a compression. Okay, so here you need to remember, so here if it is a denser medium, then what happens? These particles exert force on the denser medium, and therefore denser medium will also exert a force on these particles, so they are compressed back. Rarer medium can't do that. Okay, and that's why you can say the compression gets reflected as rarefaction and rarefaction gets reflected as a compression. So there is phase shift. This is opposite to what we have seen in case of transverse waves. So there is a phase shift of pi radians. Okay, this thing is clear. All right, next is vibration of air columns. Okay, so now see, just like we have seen the vibration of a string, okay, we'll see vibration of air columns. So suppose this is a pipe which is closed at one end and it's open at other end. This is a pipe which is closed at this end, it's open at the other end. Okay, so what will happen at the closed end? Suppose this is a pipe, okay, and what you do, this is your pipe, right? Can you imagine this? Or see what is there? This is a pipe like this. Here we have a pipe like this, okay, and this end of the pipe is suppose closed, this end is open, right, and the pipe is kept, so it is kept in this way. Okay, it's made horizontal. So now you take a tuning fork, okay, you hammer it on a rubber pad, keep it over here, the prongs of tuning fork will vibrate like this, and because of that compressions and rarefactions will be set in this pipe. And then what will happen? So see, compressions and rarefactions are set. Now you can imagine this end has maximum room for displacement because it is open end, and this end has no room for displacement of particles. Okay, so here there is an incoming wave and a wave gets reflected. So the superimposition of incoming and reflected waves form stationary waves. Okay, so that way stationary waves are formed in the pipe, right? So now in case of this stationary wave, what will happen? A compression will be formed at the closed end, and a rarefaction will be formed at open end, because here there is no room for displacement of particles. Particles will come very close to each other, and here the particles can oscillate like this. Okay, particles can oscillate, right, like this. So there is room for displacement. So therefore there will be rarefaction at this end. So now see, this is drawn, this compression and rarefaction. Now it's not good to draw, I mean it's not convenient to draw that many lines, right? So what we do is we represent compression by a node, that means particles are not moving, and rarefaction by an antinode. Okay, rarefaction is denoted by an antinode. Okay, this thing is clear, everyone? Okay, compression is denoted by a node and rarefaction by an antinode. Okay, and then good. So then see how much is the distance over here. So the distance between two nodes we have studied, it's equal to lambda by 2. What is the distance between a node and antinode? It's equal to lambda by 4. Okay, that distance is equal to lambda by 4, right? So after that, now we can find out the different modes of vibration of this air column. In a closed pipe, first we'll see a closed pipe. So for the fundamental mode, we'll have one node and one antinode, that means one compression, one rarefaction. Okay, so one node and one antinode means the length of this closed pipe is equal to lambda by 4. Okay, length of this closed pipe is equal to lambda by 4. Okay, and then there is a little nomenclature. So compression is called as pressure antinode but displacement node. So we have seen it is called as displacement node, that means particles cannot get displaced, but it is called as a pressure antinode. Why is it called as a pressure antinode? Because pressure at that point would be very high. High means it is antinode, right? High means it's an antinode. Okay, and pressure here is very low, that means it is pressure node, but the particles are very free to get displaced, and therefore there is a displacement antinode. Okay, so displacement antinode is known as a pressure node. This thing is clear, everyone? Just a little definition, right? Okay, so we have seen the I'm sorry. Okay, if L is the length of this pipe, then for a fundamental mode, what is this length? Length is equal to just lambda by 4. Lambda is the wavelength of the fundamental mode. Okay, so for closed pipe, we have seen fundamental mode has the relation between length and wavelength is length of the pipe is equal to lambda by 4. Okay, and therefore lambda is equal to, we can say, 4L, and we can make use of V is equal to F times lambda, right? So F is equal to V by lambda, and lambda is 4L. So therefore what is the frequency? Frequency over here, frequency of fundamental mode, it is just V upon 4L, right? It is just V upon 4L. Okay, and then now what is V? So we need to remember this formula. V is F is equal to what? Okay, so what is the frequency of fundamental mode? It is equal to V divided by 4L, because lambda is equal to 4L, right? So we need to remember this formula, F is equal to V divided by 4L, and also we need to remember that V is equal to what? We have studied this earlier. So speed of longitudinal waves in air, it's given by gamma, square root of gamma times p divided by rho. Okay, so if you just substitute that, you get F is equal to 1 upon 4L multiplied by V, and what is V? It is square root of gamma times p divided by rho. Okay, this thing is clear, everyone? Alright, so remember this formula too, or whenever required we can just substitute value of V, which is equal to square root of gamma times p divided by rho. It is just speed of longitudinal waves. Okay, so this is the fundamental mode. Then let's come at the second mode of vibration. Now what will happen in case of second mode of vibration? So at the closed end there will be always a compression, and at open end there is always a rarefaction. So there is always a node over here, always an antinode over here, and in between, in the first mode there was nothing. Okay, no node, no antinode. Here one node, one antinode will be formed. That means one compression and one rarefaction will be formed, right? So this is second mode of vibration. Okay, so how much would be the length of the pipe here in terms of the wavelength? So we know this much length is lambda by 4. Okay, distance between a node and antinode, and distance between two nodes is lambda by 2. So lambda by 2 plus lambda by 4 means it is 3 lambda by 4. Okay, lambda by 2 plus lambda by 4, it is 3 lambda by 4, right? So we call this wavelength as lambda 2, and therefore what would be lambda 2? So lambda 2 is just equal to 4L divided by 3. Lambda 2 is just equal to what? 4L divided by 3. Okay, this is clear, right? And then you can just substitute that in this formula. So F is equal to V by lambda. So the frequency of second mode, let's call it F2, it's equal to V divided by lambda 2. And what is lambda 2? It is 4L divided by 3, so that 3 goes to the numerator, and therefore you have F2 is equal to 3V divided by 4L. Okay, F2 is equal to 3V divided by 4L, right? And this is just equal to 3 times of V upon 4L. So this is equal to 3 times of the fundamental frequency. Okay, it is equal to 3 times of fundamental frequency. So what harmonic is this? This is third harmonic. Okay, harmonic means just a multiple of fundamental frequency. What multiple it is this? It is just 3 times of fundamental frequency. So this is third harmonic, right? This thing is clear. All right, good. So now this is a first frequency higher than the fundamental frequency. Okay, so this is called as first overtone, and first overtone here is what? It is third harmonic. Okay, then similarly we can find out here is the third mode. Overtone meaning it's the first frequency. First overtone is first frequency higher than the fundamental frequency. Okay, if you say the fundamental frequency is a tone, then overtone means higher tone. Okay, the frequency higher than fundamental frequency. This is clear? Okay, and see, first, what is the frequency? It's V divided by 4L. It's the first frequency. This air column can vibrate with this much frequency. Then with what frequency can it vibrate? It can vibrate with frequency equal to 3 times of V upon 4L. Okay, so this is equal to 3 times of F, right? This is equal to 3 times of F. Okay, so this is the third harmonic because it is just 3 times F, 3 times fundamental frequency, but it is the first frequency higher than the fundamental frequency with which this air can vibrate, air column can vibrate, and therefore it is known as first overtone. Okay, good. So first overtone here is third harmonic, right? All right, next is the third mode of vibration. So in case of third mode of vibration, what happens? There will be another extra node and antinode. Okay, so length here can be written as 5 times lambda by 4, right? Because this much distance is lambda by 4, then this is lambda by 2. Lambda by 2 means this is 1 lambda, right? A crust and trough you can say. Okay, so this is 1 lambda. Lambda plus lambda by 4 means what? 5 lambda by 4. Okay, lambda plus lambda by 4 is 5 lambda by 4. Okay, and therefore now substituting that, you get the frequency of this mode, third mode, is equal to 5 times of F. Okay, so this is third mode, right? But this is fifth harmonic. Okay, because frequency is 5 times F, and this is second frequency higher than the fundamental frequency, and that's why this is called as second overtone. Right, this thing is clear? Okay, good. All right, so now we need to remember this, that frequency of nth mode of vibration, it is just equal to 2n minus 1 times the frequency of fundamental mode. Why? Because see, the frequency of first mode is f, frequency of second mode is not 2f, it is 3f. So there is no 2f coming. Okay, there is no even harmonic here. Even harmonics are not present, only odd harmonics are present. So first frequency is f, frequency of second mode is 3f, frequency of next mode is 5 times f, so on and so forth. Okay, this is clear, everyone? And that's why it is 2n minus 1. Put n equal to 1, you will get 2n equals to 2. 2 minus 1 is 1, 1f. Put n equals to 2, so this is second mode. That means 2 times 2 is 4, 4 minus 1 is 3, okay, 3 times f, right? And what about the nth overtone? So nth overtone is just 2n plus 1f, okay, nth overtone is 2n plus 1f. So see, for an example, first overtone, put n equal to 1 here, so this thing becomes 3, first overtone is 3 times of f, right? So these are the formulas that we need to remember. Okay, good. So this is the pipe closed at one end. Next is pipe open at both ends. So this is just called as open pipe. Okay, this is just called as an open pipe. Okay, so here this is an open pipe. So this end is open, this end is also open. So what is formed at open end? Rarefaction, right? Rarefaction is formed at the open end. So that means there will be rarefaction here, there will be a rarefaction here, and in between two rarefactions. So if there is just rarefaction, that's nothing, right? So in between these two rarefactions, a compression is formed, okay? And we have seen compressions are denoted by node and rarefactions by antinode, okay? All right, so then how much would be this length? This is the length of this pipe or tube, you can say. And what's the relation between length and wavelength? Wavelength of this wave? Tell me. See, this much distance is lambda by 4. We have seen distance between node and antinode is lambda by 4. This is again lambda by 4, right? This is lambda by 4. So lambda by 4 plus lambda by 4 means 2 times lambda by 4, that is lambda by 2. Okay, this is clear, right? So length of this pipe is equal to what? Lambda by 2. Okay, length of this pipe is equal to lambda by 2, and therefore what would be lambda? Lambda is just equal to 2L. Okay, lambda equals to 2L, and you substitute that in this formula. So frequency of fundamental mode is just V by lambda, and lambda here is equal to 2 times of L. So the frequency of fundamental mode of vibration of open pipe is what? V divided by 2L. Okay, for the fundamental mode, what is the frequency? For a closed pipe, it is V divided by 4L. Okay, so if you have pipe of same length, then for open pipe, the frequency is V upon 2L, means the frequency of open pipe is twice as that of frequency of the closed pipe. Okay, frequency of the open pipe is 2 times as that of frequency of the closed pipe. Okay, good. Then we can see in case of second mode, what will happen? Again, a rarefaction will be formed at both ends, and then there was no loop in between, there was only one node. Now a loop is formed, right? But remember, what does it mean by this node and loop, etc.? Node antinodes. So Always remember, this node means compression, antinode means rarefaction. Okay, there is a okay. So then one loop is formed. Let's talk it this way only. A loop is formed because this is simple to imagine. Okay, so what would be this much length then? This length is equal to lambda by 4. This much is lambda by 4. Lambda by 4, that is lambda by 2. And this much length of one loop, we know it is equal to lambda by 2. So lambda by 2 plus lambda by 2 means it is just lambda. Okay, so length of this second mode, okay, in second mode, length of the pipe is just equal to what? The wavelength. Okay, you substitute that, so you get frequency is equal to V divided by lambda. Okay, V by wavelength, and wavelength is just equal to length of the pipe, and therefore you have frequency equals to V upon L. Frequency is just equal to what? V upon L. This thing is clear, right? And therefore what is the frequency of second mode? It is just 2 times of V divided by 2L. Okay, so it is 2 times of the fundamental mode, right? So frequency of second mode is 2 times of fundamental mode. Similarly, we can see that frequency of third mode would be 3 times of fundamental mode, so on and so forth. So open pipe is just like a vibrating string. There is no difference. All harmonics would be present here. Even harmonics are present, odd harmonics are also present. Okay, where are they absent? In case of a closed pipe, only odd harmonics are present, even harmonics are absent. Okay, in case of open pipe, the frequency is F, next one is 2F, next one is 3F. Okay, so is this thing clear, everyone? All right, good. So then there is an experiment based on this, which you might have seen. It is called as resonance tube experiment. Okay, so what do they do in case of the resonance tube experiment? So there is a tube or a pipe which is filled with water, partially filled with water, and then what you do, you take a tuning fork and you make it vibrate. You keep it on top of this pipe, and then the air column inside the pipe begins to vibrate. So either it can vibrate in the fundamental mode or in the second mode, in third mode. So this is just like, because of the presence of water, it is just like a pipe closed at one end, right? This is a pipe closed at one end. Okay, so now see here, suppose you want to find out the frequency of this tuning fork. How will you find it out? So you know, for the fundamental mode, the vibrating length would be equal to what? Lambda by 4. Okay, then for next mode, it will be equal to 3 lambda by 4. But now we don't keep the vibrating length same. Instead, what we do is we increase this length. That means we release some water. Okay, we remove some water from this tube, so vibrating length would increase, right? Vibrating length would increase. So what we do is we find for the same wavelength, what would be the second mode. That means we don't change the wavelength. What we change is we change the vibrating length. Okay, right? So then for the same wavelength, this vibrating length would be equal to what? L would be equal to 3 times lambda by 4 for the second mode. Okay, so suppose the first length is L1, second length is L2, then first length is lambda by 4, second one is 3 lambda by 4, and what would be the difference between them? It will be equal to lambda by 2. Okay, 3 lambda by 4 minus lambda by 4 is equal to what? Lambda by 2. So you get L2 minus L1 is equal to lambda by 2, right? So you find these two lengths. Okay, you know what is the speed of sound or speed of longitudinal waves in air, and then you make use of this formula. Okay, so L2 minus L1 is lambda by 2. So lambda would be equal to what? 2 times of L2 minus L1. lambda is equal to 2 times of L2 minus L1. So what would be frequency? It's V by lambda. So it is V divided by 2 times of L2 minus L1, right? It's V divided by 2 times of L2 minus L1. Okay, this is clear, everyone? Okay, all right, very good. So let us see this problem. The fundamental frequency of a closed organ pipe of length 20 centimeter is equal to second overtone of an organ pipe open at both ends. Okay, so what would be first overtone for open pipe? It is 2 times F, right? What would be second overtone? It is 3 times F. Okay, this thing is clear. So they say that for a closed pipe, frequency of a closed pipe is equal to the second overtone of open pipe. Okay, so what is second overtone for open pipe? It is 3 times of the fundamental frequency of open pipe. So we'll use suffix C for the closed pipe, suffix O for open pipe, right? So then the length of organ pipe at both ends is, and length of this closed pipe we know it is 20 centimeters, that's given. Okay, so what is the fundamental frequency here? It is V divided by 4L for the closed pipe. So it is V divided by 4LC, C for the closed pipe, and it's equal to 3 times of V divided by 2 times LO. Okay, LO for the open pipe, right? So then VV gets cancelled. First of all, VV gets cancelled, and you want length of the open pipe. So length of open pipe, so just cancel out that 4 with this 2, so 2 will remain here. So it is 2 times of LC, and this 3 will also go. Okay, so 3 will go in denominator on that side, so it is 2 times of 3 means 6. So length of open pipe is 6 times of length of closed pipe, and that is equal to what? 6 times of 20 means it's 120 centimeter. Okay, very simple, right? Everyone? Okay, good. Then let's see next one. An air column closed at one end and open at other resonates with tuning fork when the smallest length of column is 50 centimeter. Okay, smallest length of column is 50 centimeter, and it is open at one end and closed at another. The next larger length of the column resonating with the same tuning fork is. So we have just seen this. Okay, means frequency is same, so wavelength would be same. So what is the vibrating length of first mode? Let's say this is closed end. So vibrating length of the first mode, tell me. It's option A. All right, let's see. Vibrating length of first mode L1 would be equal to lambda by 4, right? This is lambda by 4. Okay, and then what would be vibrating length of the second mode? So in second mode, will be would be like this, right? This is lambda by 4 and this is lambda by 2, so that is 3 lambda by 4. Okay, so L2 is 3 lambda by 4. That means it is just 3 times of L1. What was L1? L1 is 50 centimeter. So L2 would be equal to 3 times of 50. So that's good. Very good, Selva Kumar. So it is 150 centimeters. Right? This thing is clear. Okay, good. All right. Then let's see next. Okay. The second overtone of an organ pipe has the same frequency as first overtone of a closed pipe L meter long. Okay, second overtone of an organ pipe has same frequency as first overtone of a closed pipe. So both are overtones. Okay, so second overtone means second overtone of open pipe. So what is second overtone of open pipe? Let's write it. Second overtone of open pipe is equal to first overtone of closed pipe. So here frequency of the fundamental mode is V by 2L. Okay, and second overtone is just 3 times of that. First overtone is 2 times in case of open pipe, second overtone is 3 times. And here the frequency of fundamental mode is V divided by 4LC, C for the closed, okay, length of closed pipe, so suffix C, and first overtone itself is thrice. Okay, there is no even harmonic, right? So first overtone is 3 times of V upon 4LC. Okay, so 3V gets cancelled out. You have 2L0 is equal to 4LC. That means L0 is equal to 2 times LC. So that's very simple, right? L0 is equal to 2 times LC. Okay, then length of open pipe will be, so it is 2 times of L. That's answer, right? This is clear. Okay, good. All right, then let's see next one. The two nearest harmonics of a tube closed at one end and open at other are 220 Hz and 260 Hz. So we have seen in case of a resonance tube experiment, right? Okay, let's read the question first. What is the fundamental frequency of this system? All right, so let's find out fundamental frequency. F is just equal to what? F is equal to V divided by, okay, before that, sorry. So what is the frequency difference between what is the frequency difference between two nearest harmonics of a closed pipe? Tell me. Okay, so for an example, you take fundamental mode, the frequency is F. Okay, what is the frequency of next mode? It is 3 times of F. What is the frequency of next mode? It is 5 times of F, right? So in case of a closed pipe, fundamental mode has frequency F, next mode has frequency 3F, next one has frequency of 5F. So frequency difference between any two nearby modes. So let's say frequency of nth mode, okay, minus frequency of n minus 1th mode, right? So that is equal to what? 2 times of F. Yes, no? Okay, then that's very simple. So frequency of nth mode is suppose 260 Hz, n minus 1th mode is 220. So it is 260 minus 220 is equal to 2F. So that's 40. 40 is equal to 2F, means F is equal to 20 Hz, right? All right, good. So this is very simple. Okay, let's see next one. The fundamental frequency in an open organ pipe is equal to third harmonic of a closed organ pipe. See, all problems are similar, right? Fundamental frequency of open organ pipe. So let's say FO is equal to third harmonic of closed pipe. So that is just 3 times of FC. Okay. The length of closed pipe is 20 centimeters. So put the length. And length of open organ pipe is. Okay, so what is this? This is V upon 2 times of LO, that's fundamental frequency of open pipe, and this is just V divided by 4 times of LC, okay, fundamental frequency of closed pipe, right? So VV gets cancelled, and you can move this 2 on this side, so 4 by 2, okay, so 2 will remain, and then take reciprocal, so you get LO is equal to 2 times of LC divided by 3. So that is 2 times of, what's the length of the closed pipe? 20 centimeters. So 2 times of 20 divided by 3. So that is 40 by 3. How much? 13.2, right? It will be 13.3, something like that. 13.2 centimeters. Okay, that would be the answer. This is clear? Okay, good. Let's see next one. A tuning fork is used to produce resonance in a glass tube. The length of the air column in this tube can be adjusted by a variable piston. Okay, at room temperature of 27 degrees Celsius, two successive resonances are produced at 20 centimeter and 73 centimeter of column length. If the frequency of tuning fork is 320 Hz, then the velocity of sound in air at 27 degree is. So see, here a tuning fork is used to produce resonance in a glass tube. The length of air column in this tube can be adjusted by a variable piston. Okay, you are adjusting the length. So at room temperature, resonances are produced at 20 centimeter and 73 centimeter of column length. Okay, then if the frequency of tuning fork is this much, 320 Hz, then what would be the velocity of sound at 27 degrees Celsius? This is the question. Alright, so tell me, what can we do here? So what is L2 minus L1? Remember, what is L2 minus L1? It is lambda by 2, right? For two successive resonances, okay, for two successive resonances, if lengths are L1 and L2, what's the difference in length? It's equal to lambda by 2. So one is 20, another one is 73. So lambda by 2 would be L2 minus L1. So lambda is just equal to what? 2 times of L2 minus L1. Just find it out. So it is 2 times of L2 is what? 73, L1 is 20, and it's in centimeters, so convert it in meters, multiplying with 10 raised to minus 2. So this is 73 minus 20 is 53, 53 times 2 is what? 106. 106 multiplied by 10 raised to minus 2, okay, 10 raised to minus 2, and this will be in meters. That's the wavelength. And then what is speed? Speed is just frequency times wavelength. So frequency of the tuning fork is 320, okay, so f times lambda, and f is 320, so 320 multiplied by 106 into 10 raised to minus 2, so that would be equal to little greater than 320, okay, 320 times, you can say 1.06. Tell me what's the answer? Is it 330? Yes. 330 or 339? Which one?
Sir, 339.2, sir.
Oh, it's 339. So, okay, good. So 339 meters per second is the answer. right? So it is option B. So this one is also simple, right? Yes, no? Okay. All right, good. Let's see next one. A tuning fork with frequency 800 Hz produces resonance in resonance column tube with upper end open and lower end closed by water surface. Successive resonances are observed at lengths this one, and this one. The speed of sound in air is again similar to the last problem. Okay, V is equal to what? Let's take L1, L2 and L3. So we can say V is just equal to this frequency multiplied by lambda. And what is lambda? So it is 2 times of either you take L2 minus L1 or you take L3 minus L2. Okay, so let's take L3 minus L2. So what's that? Frequency is 800 times 2 multiplied by L3 is 52.75 minus L2 is 31.25, and that's in centimeter converted to meter, so 10 raised to minus 2. So what's the difference? It's 21.5, right? The difference between them is 21.5. Okay, 21.5 times 2 would be, or yeah, 40, 42, it would be 43, 43 times 8. Okay, find it out. 50 times 8 will give me 400, right? 400 minus 7 8 is 56, yeah, 344, right? 344 meters per second. That's the answer. Okay, this is clear. All right, so next let's talk about the beats. So what are beats? So beats are alternate waxing and waning. It's called as waxing and waning of the sound. So actually it is big sound, then no sound, big sound or very little sound, right? So you know what are beats. Okay, we hear it every day. I mean, you must have heard beats on DJs, right? So big sound, no sound, big sound, no sound, that is beats. How is it produced? So if you have two sound waves having the same amplitude, nearly same amplitude you can say, and slightly different frequencies. So this thing is important, they have slightly different frequencies. Then what happens is, if you play them together, or you have any two waves, okay, any two transverse waves, even transverse waves. So if they come at one point of the medium, okay, simultaneously, then what happens is the resultant wave would be the maxima and minima. Okay, so what will happen? A wave, the resultant of these two will be a wave having maximas and minimas, alternate maximas and minimas. Okay, so there is a big sound, you can say, no sound, again big sound, no sound. So the frequency of this wave, resultant wave, is just equal to the average frequency of these two interfering waves. Okay, superimposing waves. So f is just equal to f1 plus f2 divided by 2. And then what about the frequency of maximas and minimas? That is frequency of beats. So the frequency of beats is just equal to f2 minus f1. Actually you can say the absolute value of f2 minus f1. So suppose here you have two waves. The frequency of first one is 500 Hz. Frequency of second one is 505 Hz. Then what happens? The beat frequency is just 505 minus 500. So it would be equal to 5 Hz. And what is the frequency of this resultant wave? It's just equal to average of the two, that is 500 plus 505 divided by 2, that is 502.5 Hz. Okay, this thing is clear. All right, good. So in nutshell, this is beats, and most of the questions are just based upon this much theory, right? If two sound waves arrive at a point simultaneously, their frequencies are different, then what happens? Alternate big sound and no sound, that means waxing and waning is formed, and that is known as beats. What is the beats frequency? Beats frequency just frequency difference of those two sound waves, and the resultant frequency, see here there is one resultant wave whose frequency is equal to average of the two frequencies, but the amplitude of that resultant wave gets it becomes big and small, right? Amplitude keeps on changing. The variation in amplitude has frequency equal to this much. That is known as beats frequency. Okay, that one is known as beats frequency. This thing is clear? Okay. So then now let's consider two waves. Okay, so y is equal to a sine of omega 1 t minus k1x, this is the first one, and y2 is equal to a sine of omega 2 t minus k2x, this is second one. Put x equal to 0, right? Fix some point. Okay, so x equal to 0, this is a point of a medium for simplicity. Then they just become y1 is equal to a sine of omega 1 t, y2 is equal to a sine of omega 2 t, because x is equal to 0. Okay, so then now what happens? So resultant wave at that point will have oscillations equal to what? Given by displacement of the resultant oscillations is given by y1 plus y2, sum of the two displacements, and that is equal to then a multiplied by a, you can take common, right? So sine omega 1 t plus sine omega 2 t, and then you have this formula sine a plus sine b. Okay, so that is 2 sine of a plus b by 2 multiplied by cos of a minus b by 2, and that's it. So y is equal to, you have 2a multiplied by sine of omega 1 plus omega 2 by 2 into t, and multiplied by cos of omega 1 minus omega 2 by 2 into t. Okay, so then you can see we'll write this omega is the average angular frequency, and we write it as omega 1 plus omega 2 by 2. Okay, then what happens is we get, see, resultant wave will have the equation as 2a multiplied by, you have cos of omega 1 minus omega 2 by 2t multiplied by the sine of omega t. Okay, sine of omega t. So here, see, what is the amplitude of this one? It's like you have a wave whose frequency is equal to what? Omega, which is equal to omega 1 plus omega 2 by 2, and whose amplitude is this one. This is the amplitude r, which is 2a multiplied by cos of omega 1 minus omega 2 by 2 into t, right? This is the amplitude. Okay, I'm sorry, and this amplitude is given by what? 2a multiplied by cos of omega 1 minus omega 2 by 2 into t. Okay, and you can very easily see that cos function or sine function, it will hit 2 times the maximum and minimum values, right, in one cycle. If you consider one cycle, how many times will it hit maximum and minimum values? 2 times, right? Yes, no? Okay, so this is positive maximum, this is negative maximum. This thing is clear? Everyone? Okay, so if this is the frequency, of a wave, let's say this is omega prime is equal to omega 1 minus omega 2 by 2, this is the angular frequency. Okay, so if one wave is formed, how many times the maxima and minimas would be formed? 2 times. So that's why if this is the frequency of this amplitude, okay, so omega prime is omega 1 minus omega 2 by 2, then you have, see, then you have the frequency of beats, that means in one wave 2 bits are formed, so that would be equal to 2 times of omega 1 minus omega 2 by 2. The 2 will get cancelled, and you can very easily see that the angular frequency would be equal to omega 1 minus omega 2, and therefore the frequency of beats would be equal to what? it will be equal to f1 minus f2. Okay, the difference between them. This thing is clear? Yes, no? Okay, so this is one way uh, of looking at this, and then or we can solve it. So see, there is another way. So now loudness or the intensity of the resultant wave would be just equal to what? Intensity we know, it's directly proportional to amplitude square. So it is some constant k times r square. Okay, and what is r? Or you can make k equal to 1 also. So r is this one, take square of that, so it will be 4a square multiplied by cos square of this thing, omega 1 minus omega 2 by 2 into t. Okay, and then you remember this equation, 1 plus cos 2 theta is equal to 2 cos square theta, right? So you have cos square of this thing. Okay, you have cos square of this thing. This thing can be written as what? 1 plus, okay, this is your theta. Okay, so this thing is your theta, omega 1 minus omega 2 by 2 into t. This is your theta, and you have cos square of that. So you can write 1 plus cos 2 theta is equal to 2 cos square theta, right? So this cos square theta can be written as what? 1 plus cos 2 theta divided by this 2. Okay, so you write 1 plus cos of 2 times of this thing, that is 2 times of omega 1 minus omega 2 by 2 into t, okay, divided by 2 would be this cos square of theta. This thing is clear? Everyone? Right? And then the 2 moves out. Okay, so therefore now what would be the resultant amplitude? So it will be 2 times of a square, right? 4 by 2 is 2, 2 times of a square, 1 plus cos of this 2 by 2 is 1, so 1 plus cos of omega 1 minus omega 2 times omega 1 minus omega 2 times t. Okay, right? So you can say when this cos of omega 1 minus omega 2 times t is minus 1, okay, when this thing is minus 1, then what would be the resultant amplitude or resultant intensity? Then it would be equal to 0, because 1 minus 1 would be equal to 0. Okay, and when this is equal to plus 1, when it's equal to plus 1, then the resultant amplitude is maximum, because it will be 1 plus 1, okay, that is 2 times of this thing. Okay, it will be 4a square. So resultant amplitude would be maximum, resultant intensity would be maximum, right? Okay, so 4a square, that is you have maxima. So what you get is angular frequency of I is equal to omega 1 minus omega 2. Okay, and therefore what would be the frequency? The frequency of beats would be equal to f1 minus f2. Angular frequency is omega 1 minus omega 2, therefore the beats frequency would be equal to f1 minus f2, right? This thing is clear? Everyone? Okay, so beats frequency is f1 minus f2. Okay, and then what would be time period of beats? So time period of beats is 1 by n. Okay, n is the beat frequency, it's f1 minus f2. So time period of beats would be equal to 1 by n. So it is 1 by f1 minus f2. Okay, right, this is clear, everyone? All right, good. Okay, so then let us see some problems based upon this thing. Okay, so let's see this one. For production of beats, the two sources must have, tell me, different frequencies and same amplitude, different frequencies, same amplitude and same phase, different frequencies and same phase. Tell me. Different frequencies and same amplitudes, right? Okay. So now different frequencies and same amplitudes. This is clear. Actually, when you have different frequencies and the same amplitude, then clean beats would be formed. Even if you just have different frequencies, amplitudes are different, then maxima would be a big sound, but minima won't be equal to zero sound. Okay, minima won't be equal to zero sound. We'll see that in one of the questions. Okay, but for clean beats, we should have different frequencies and same amplitude. Okay, let's see next one. Wave has simple harmonic motion whose period is 4 seconds, while another wave which also possesses simple harmonic motion has its period 3 seconds. If both are combined, then the resultant wave will have the period equal to. Tell me. First one has period equal to 4, second one has period equal to 3. Okay, so see, when two waves are they come at same point, it's option C. Okay, let's check. Two waves come at the same point, then what will happen? Then the beats are formed, and what is beats frequency? It is f1 minus f2. Okay, right? So this is just 1 by t1 minus 1 by t2. Okay, so let's take absolute value. So it is 1 by, what is time period of first one? It's 4. 1 by 4 minus 1 by time period of second one is 3. So that is equal to, yeah, so in denominator we'll have 12. So this is 3 minus 4, that's minus 1 by 12. Or if you take it outside of absolute value, it will be 1 by 12. So this is the frequency. This is the frequency of beats. And therefore, what would be time period? The time period would be equal to 12 seconds. So that's correct. It is option C. Right? This is simple. Alright. Let's see next one. Two sound waves with wavelengths 5 meter and 5.5 meter respectively, each propagates in a gas with velocity of 330 meters per second. We expect the following number of beats. Okay. So how many beats? N is equal to just f1 minus f2. Right. But what is given here? Wavelengths are given. Wavelength of the first one is 5 meter. Wavelength of second one is 5.5 meter. And also the speed is given. Okay. So what is the frequency? It is velocity divided by wavelength. So v by lambda 1 minus v by lambda 2. Okay. So that is 330 divided by wavelength of first one is 5 minus 330 divided by 5.5. So what is 330 by 5? 66. And 330 by 5.5 would be, is it 60? Okay, so let's put one more 0, so this would be 55, then divide by 11, so this would be equal to 300 and this would be equal to 5. Yeah, so it is 60. So this is 66 minus 60 means 6 hertz. Okay, so how many beats are formed? 6 beats are formed, right? This is clear? Yes, no? Okay, it's simple. Alright, good. Let's see next one. Two vibrating tuning forks produce waves given by y1 equals to 4 sine of 500 pi t and y2 equals to 2 sine of 506 pi t. Number of beats produced per minute is, how many beats are produced per minute? Tell me. So just compare that. Okay, so y1 is 4 sine of 500 pi t. So this will be equal to omega 1 is 500 pi, right? That is 2 pi n1 is equal to 500 pi, and then you can divide this thing by pi. So 2 times n1 is 500, that means n1 is equal to 500 by 2 means 250 hertz. Similarly, compare this one with a sine of omega 2t. So your omega 2 would be equal to 506 pi, right? Omega 2 is equal to 506 pi, that is omega 2 is 2 pi times n2, that is 506 pi, and then pi and pi will get cancelled. So n2 would be equal to 506 by 2. So n2 is 253. So when these two are played together, how many beats are sorry, how many beats are formed? 3 beats. That's very simple, right? That is the answer. Okay, that's simple. Let us see next one. Each of the two strings of length 51.6 centimeter and 49.1 centimeter are tensioned separately by 20 Newton force. So you have two strings, okay, some tension is given, mass per unit length of both strings is same, and it's equal to 1 gram per meter. When both strings vibrate simultaneously, the number of beats is, okay, so tell me, again number of beats would be equal to what? F1 minus F2, right? So what would be F1? So these are strings, this is a vibrating string. So frequency of the first one would be 1 upon 2L multiplied by square root of T by mu. Okay, so tension is given, it's 20 Newton. Mu is given, it's 1 gram per meter, but we need to convert it. So let's convert it to kg per meter. So it's 1 gram per meter. That means 10 raised to minus 3 kg per meter. Okay, and then put the values. So what would be F1? It's 1 upon 2 times L1. Okay, so let's take this one as L2. This is suppose L2 and this one is L1. Okay, 1 upon 2 L1 times square root of T by mu. T by mu is same for both of them, right? Minus 1 upon 2 L2 times square root of T by mu. So let's take 1 by 2 times T by mu common. Then you have 1 by L1 minus 1 by L2. What is that? 1 by 2, okay, square root of T by mu. So that's 20 divided by, this is 10 raised to minus 3 in denominator, right? And then you have 1 by L1. So what is L1? Let's take this one as L1, okay, so it's 49.1. Beats will be same, but if you divide by a smaller number, then answer would be bigger. Okay, so result would be automatically positive. So 49.1, but that is centimeter, so multiply that with 10 raised to minus 2. So 10 raised to minus 2 in denominator would be equal to 10 raised to plus 2 in the numerator. So minus, you have 10 raised to 2 divided by 51.6. Okay, then there is some calculation. So I will just take this on the next page. Right, so this is your n, it's equal to, see, then you have this 10 square also common, so that is 100, 100 by 2 is 50. Okay, and then you have square root of this thing. This 10 raised to minus 3 goes to the numerator, becomes 10 raised to plus 3. So that thing can be written as 2 multiplied by 10 raised to 4. 2 multiplied by 10 raised to 4. Then what remains is this thing. Okay, so let's do cross multiplication. We have already taken 10 raised to 2 out. So it's 51.6 minus 49.1 divided by 49.1 times 51.6. Okay, so this thing would be nearly equal to 50 times 50 because first one is a little bit lesser than 50, next one is a little bit higher than 50. So roughly we can say it's 50 times 50. Okay, and this 100 by 2 would be equal to 50. So this is equal to 50. Let's cancel it out with one of the 50s over here. Okay, and then what remains? Root 2 multiplied by, take square root of 10 raised to 4. So it is 10 raised to 2 multiplied by, you have 51.6 minus 49.1. Okay, so it is 2.5. Right, this thing is 2.5. 51.6 minus 49.1, that is 2.5. Okay, so 2.5 times 100 is 250, 250 root 2. So 1.41 multiplied by 250. What's the answer? 250 times 1.41. Did we do some mistake in point somewhere? Oh, this 50 is left, no? 150 is left. Divided by 50, divided by 50. So this thing would be equal to 5. 5 multiplied by 1.41. How much? Nearly equal to 5 times 1.5 would be equal to 7.5. It's less than that. So it will be equal to 7. Nearly equal to 7, I can say. That's correct, right? It's option A. This is clear? Yes. This is just some calculation, right? Okay, good. All right, let's see next one. Two sources of sound placed close to each other are emitting progressive waves given by y1 is equal to 4 sine of 600 pi t, y2 is equal to 5 sine of 608 pi t. An observer located near these two sources of sound will hear how many beats? Okay, so this is 600 pi t, this is 608 pi t. So you have omega 1 is equal to 600 pi, that is, let's move this here, that is 2 pi n1 is equal to 600 pi, right? So this pi gets cancelled, 600 divided by 2 means 300. So n1 is equal to 300. Similarly, what would be n2? So we have 2 pi n2 is equal to 608 pi. Okay. Therefore, what would be n2? So n2 is equal to 608 by 2. So 304 hertz. So how many beats are formed? That is difference between frequencies of these two. So 4 hertz are formed. 4 beats are formed. Right. And then now what would be 4 bits are formed? So it is option A or option D. And what would be the ratio? Okay, ratio of intensities. So you know what is ratio of intensities? There are two different amplitudes of two waves. Okay, maximum intensity is I1 plus I2 plus 2 times of square root of I1 I2. And you know frequency is intensity is directly proportional to amplitude square. So amplitude of first one is 4, square of that is 16. Amplitude of second one is 5, square of that is 25. So this thing would be 16 plus 25 plus 2 times of square root of 16 times 25. And that, you know, what's that? So square root of 16 is 4, square root of 25 is 5, 5 times 4 is 20, 20 times 2 is 40, okay, and this thing is equal to what? 41, 41 no, 41 plus 40 is 81, so 81. And what would be I mean? I mean is equal to I1 plus I2 minus 2 square root of I1 I2, right? What is this thing? So the calculation is just same as that of this one, but there would be one negative sign here. So this is 41 minus 40 means it's equal to 1. Okay. So what's the ratio of intensities? The ratio of intensities would be equal to 81:1. So it is 4 beats, right? Because the frequencies are 300 and 304. So 4 beats, but the intensities would be 81:1. Okay, so it is option D. This thing is clear? Everyone? Yes, Orna, is it clear? Good.
Yes, sir.
Good. Let's see next one. A source of unknown frequency gives 4 bits when sounded with a source of known frequency 250 Hz. The second harmonic of the source of unknown frequency gives 5 beats per second when sounded with a frequency of 513 Hz. The unknown frequency is. Okay, so these kind of problems are repeated. Okay, so pay attention. You have source of some frequency which gives 4 bits with 250 Hz. So f must be either 4 Hz higher than that. Okay, that means 250 plus 4, that is 254, or 250 minus 4, because it gives this thing would be 246, because it gives 4 bits with 250 Hz. Okay, source of known frequency 250 Hz, right? So it must be, f must be either 4 Hz higher than that or 4 Hz lower than that. Then the second harmonic of the source, okay, so 2f gives how many beats? 5 beats with 213. Okay, so either it should be 213 plus 5 or it should be 213 minus 5. Okay, so this thing gives 218 Hz, this one gives 208 Hz. Okay, so now so 2f must be twice of f, so either f is this one or this one, but then if you take twice of f, it should match with one of the values of these two, right? So which one matches? Oh, it was 513, no, I wrote 213. It's 513. Okay, so which one matches? If you take twice of, so 2 times of this would be what? 508. So this one matches, right? If f is 254, take twice of that, it will give what? 508. So this one matches with this one. That means what should be f? It should be 254. What should be 2f? It is 508. Okay, so what is frequency? Unknown frequency is 254 Hz. This is clear? Okay, Selva Kumar. Clear, not clear?
Clear, sir.
Okay, good. All right, let's see next one. In a guitar, 2 strings A and B made of same material are slightly out of tune and produce beats of frequency 6 Hz. Okay, when tension in B is slightly decreased, the beat frequency increases to 7 Hz. The frequency of A is 530. Again, it's similar to the last one, and this is recent one, right? The original frequency of B will be, okay, so A and B earlier they gave what? They gave 6 beats. Okay, beats frequency is 6 hertz. And what is given? Frequency of A is given. Okay, frequency of A is equal to 530. So frequency of B must be equal to 530 plus 6, or it must be 530 minus 6, because when they are sounded together, how many beats are formed? 6 beats are formed. So either it is 536, okay, 536, or it is equal to 524 hertz, right? But then when tension is B is slightly decreased, what will happen to the frequency? Tension is decreased, so we know frequency is 1 upon 2L square root of T by mu. If tension is decreased, frequency is decreased. So tension in B is decreased, means frequency of B will decrease. But then what happens? The frequency, beats frequency increases to 7 hertz. So FB prime becomes, if it gives 7 beats, that means it should be either 537 or 523, because it is giving 7 beats with this one. But then we know if tension is decreased, frequency must decrease, right? And if it is 537, this is increasing. Okay, 523 is decreasing, right? So therefore what must be the original frequency? It should be 524. Okay, this thing is clear, everyone? Right. Okay, so these kind of problems are asked on beats. Let's see one more. 3 sound waves of equal amplitudes have frequencies n minus 1, n and n plus 1. They superimpose to give beats. The number of beats produced per second will be. Okay, so this is a typical question and it was asked once. So answer of this one is C. Answer of this one would be, it will go like this. So you have these two. Okay, this is first one, second one. There would be some beats between them. How many? 1. So n produces 1 beat with n minus 1 and it produces 1 beat with n plus 1. So total number of beats would be equal to 2. Okay. So if it was n minus 2, n and n plus 2, total number of beats would be equal to what? If they are separated by same interval, then it is just the beats between first two and beats between the last two, add those. Okay, so that is your answer. This is clear? Okay, so answer to this would be 2. Right. All right. So this is beats. Okay, these kind of problems are asked, and this one was asked only once. Now suppose there is a question like this. First frequency is n minus 2, second one is 2, second one is n, and third one is n plus 2. Then how many beats would be formed? So this forms 2 beats with the first one, 2 beats with second one. So how many beats are formed in total? Total is 4 beats are formed. Okay, so that way you will give the answer. Right, this is clear, Hindusha? Suppose first frequency is n minus 2, okay, next one is n, and next one is n plus 2. Then you can say beats between these two would be 2, beats between these two would be 2. Okay, so total 4 beats would be formed. Right. Purna, this is clear? Question in the screen. oh, this one forms one beat with this one. Okay, this n forms one beat with the first one, first frequency is n minus 1, and it forms one beat with the next one. Okay, so 1 plus 1 means 2 beats. All right. Okay, so then we'll stop here. Okay, and this is the end of this chapter. Tomorrow we'll start with the next one. Welcome. Okay, then bye.